Hi everyone. For my presentation, I chose the work entitled Space Architecture Design for Commercial Suitability, a case study in in-situ resource utilization systems. The paper is from volume 175 of the journal Acta Astronautica, and the original authors are listed here. As the title implies, this work is primarily focused on space architecture design, and particularly the aspects of architecture selection. The key question that the researchers are proposing should be asked is, among the best architecture options, are there differences in commercial suitability that can be exploited? The authors feel that considering commercial suitability in addition to traditional architecture criteria will ultimately benefit not only organizations like NASA who are making these architecture selections, but also the industry as a whole. The paper is broken down into 5 sections, which are listed here. The first section is an introduction to the work, which is essentially what I'm doing now. Section 2 is a review of NASA's previous space commercialization strategies and some notes about how they've fallen short. Section 3 is the proposed concept and strategy of commercial suitability that the paper is exploring. Section 4 is a case study which kind of employs this proposed strategy in the context of lunar ISRU, and Section 5 is a further discussion and examples of potential future work. Now we'll go into the topics covered in Section 2. Section 2 of the piece covers previous commercialization strategies implemented by NASA, starting with 1979, when the major incentives to contractors were basically the utilization of NASA's current resources. The space shuttle era, between 1981 and 2011, was marked by direct investments in capabilities intended exclusively for use in space, and generally utilized defense-type contracting mechanisms which were already established at the time. An example of this is NASA's Commercial Orbital Transportation Services program, which allows them to coordinate with private companies to deliver crew and cargo to the ISS. In 2011, the National Space Policy stipulated that NASA would purchase and use commercial space capabilities and services to the maximum practical extent, which essentially means that if there was a private sector entity that was providing any of these resources, NASA would, to the best of its ability, use those services. And finally, to bring things closer to the case study of the paper, the authors describe the Commercial Lunar Payload Services program, which is using contractor-provided assets in the lunar context. The commercialization strategy proposed in this paper includes picking a specific size for a module that is common to multiple missions or that has the same standard interface, which basically boils down to standardization. And the authors believe that doing this will enable economies of scale within the space market. The authors also think that this is particularly effective when there's multiple different architectures that differ only in their commercial suitability. So really the suggestion here is to consider commercial suitability in addition to more traditional criteria for space architecture selection. And they note that a commercially suitable architecture should only be chosen if the benefits outweigh the costs of the constraint. After describing their strategy of considering commercial suitability in space architecture selection, the authors go on to employ this strategy in a hypothetical case study for an ISRU plant on Earth's moon. As described on the previous slide, the author's strategy includes standardization and the use of simpler interfaces, which they believe will enable economies of scale in the space environment and stimulate mass production. The results of their case study show that standardized modular architectures can actually reduce overall mission costs in some cases. Here we see the primary figures displaying the results of the case study. In both cases, the vertical axis is an indication of the cost of the ISRU operation. And we can see that with a lower learning curve, the commercialization strategy proposed by the authors of this paper can actually reduce the overall costs below the standard baseline. But of course, this is just a hypothetical case study, so the next question is whether these results will apply in the real-world context. And to investigate this further, I think it's worth taking a look at some of the current trends in the commercial sector. Here I've included some screenshots taken directly from the Astrobotic website. Astrobotic is a space robotics company focused primarily on lunar logistics and planetary mobility. Here we see both their Cube rover and their Polaris rover products, which can accommodate payloads in the same form factor as the CubeSat standard. So again, just as the authors describe, we see a real-world commercialization strategy taking advantage of standardization. And just to give an indication of how relevant standardization is specifically to lunar rovers, here are the program notes for a recent international symposium on artificial intelligence, robotics, and automation in space. And you can see on the right side of this table just how many talks explicitly discuss rovers. So as far as space architectures which include a rover element, we can see that this is definitely a ripe place for standardization. So I think a lot of what we've discussed and what the paper covers can be boiled down to this image, which shows that the benefits of standardization are already known in the space industry thanks to the CubeSat revolution. And those same paradigms can apply in new space endeavors like ISRU on Earth's moon. And eventually, what we get out of this is a flourishing lunar economy that has all kinds of different use cases and applications, but is enabled through the standardization and modular architecture selection. So just to reiterate the overall idea of the paper that we explored here, the suggestion is that organizations like NASA and ESA should take commercial suitability into account when they are selecting the space architectures for various missions. This will enable the economies of scale that we're used to seeing in the terrestrial technology industry to be applied in the space context and ultimately pave the way for accelerated space development. And that concludes the presentation on this paper. Thank you very much for your time and attention.